Hi again. As promised, I'm back and we're going to be talking about weak bases. So the math with the weak bases is very similar to Chapter 7 ice table, same with the weak acids. And the reason why we can use equilibrium is because, once again, weak bases do not form a complete forward reaction. They don't completely ionize, so we get to use the equilibrium arrows because they mainly stay as they are. Okay, so only about 10% of the base goes forward. And what does it mean to be a base? Well, a base is a proton acceptor. So in most cases, because our bases are in solution, they're aqueous, the proton donor will be water. Okay, and so because the proton donor is water, so let's just take a look at water for a moment. And we remove a proton, we will end up with H plus OH minus. Okay, so that's what happens with that, and that's how we end up with our hydroxide. In grade 10, we would have told you anything that had a hydroxide was a base, but now you know a better definition for bases. They are proton acceptors, and it usually happens in solution, so you're forming the OH. Okay, so when we take a look here, ammonia is our base because it accepts the proton from the water. And so in accepting the proton from the water, it gains an H and it gains the positive charge. And water, like I just showed you here, loses its proton. That's what makes water an acid. And it forms the hydroxide. So we can link these two entities together, making this the conjugate acid because the ammonium ion is now capable of donating a proton. And we can link these two together, making the hydroxide the conjugate base because it can no longer donate a proton. All right, so the general equation for this weak base dissociation is a base in the presence of an aqueous solution or water will gain a proton from the water, and water forms the hydroxide, and the conjugate acid entity gains a proton and usually a positive charge. So if we look at the equation, so once again, we've got a new constant, Kb. So that's the base constant. And this gives us products over reactants yet again. Okay, and once again, we don't include the water because liquid water is a constant concentration, which is already factored into the K constant. So let's take a look at some examples of questions, all right? So looking here, what is the hydroxide concentration? So we're going to look for the hydroxide concentration of a 0.1 molar solution of ammonia. So first things first, what you always do is you set up your equation. So we're using the same one as above, but you really should be able to apply this general formula for the ionization of a base to any base that we give you. Okay, we also know that ammonia is a weak base, so we're going to be working with an equilibrium. So ammonia gains its proton from water, and water loses its proton, forming the hydroxide. So there's my equation. So let's do our ice table. Okay, initially we start out with 1 molar solution of ammonia. We start out with none of our products. And since everything's a 1-to-1-to-1, negative x, positive x, positive x. So our change will be 0.1 molar minus x. 0 plus x equals x. 0 plus x equals x. Okay? So now we're looking for the hydroxide concentration. This is the entity we need to know. So we can use our Kb equation. Okay, we can use this to find our X. Now, you can't have too many unknowns, so what we'll have to do is we'll have to go to page, and I believe it's 726 yet again, to look up the Kb for ammonia. And when I do that, I find that the Kb for ammonia is 1.8 times 10 to the negative 5. So then I start plugging my stuff in. So NH4 is X, and we're talking equilibrium concentrations here. So X times X all over 0.10 minus X. Okay. Now, once I have this, X squared, 1.8 times 10 to the negative 5. Now, remember, we have a very small Kb. Remember how I told you anything smaller than 10 to the negative 5, you can assume that this X is negligible. Okay, so because we can assume that that X is negligible, we can take it out of our equation and simply take the square root of both sides. So what we'll do is we will have X equaling the square root of 1.8 times 10 to the negative 5 times 0.10. So, okay, so X in this situation, once we do that math, so we multiply these two first and then take the square root. And then take the square root on both sides, I will get 1.34 times 10 to the negative 3. And this will be in moles per liter because X represents a concentration. So when I find what X is, never forget X and OH stand for the same thing. So we can therefore say my concentration of OH at equilibrium is I was looking at the question. Is 1.34 times 10 to the negative 3 moles per liter. So we got that part of the question. But now we've got to figure out what the pH is. Now there's two ways to do that. You only need to show me one way, but there are two ways. So you only need to give me one, obviously, don't prove it twice. So we can do one of two things. Knowing that the concentration of hydroxide is 1.34 times 10 to the negative 3 moles per liter, we can use this equation. Okay, so once we get that, all right, once I plug that into my calculator, I get 2.87. Now there's a formula that you would have learned yesterday where pH plus POH equals 14 because we're talking about the pH scale. And, whoops, sorry about that, guys. Whoa, totally went to the whole note. Hold on. Oh, look, quadratic formula. All right, hold on. Don't get dizzy. Don't get dizzy. Here we are. Okay, whew, sorry about that. So, when we plug in because remember, I'll just bring this over and make it negative. So my pH in this situation, 14 minus 2.87 is 11.13. So I've solved it that way, which makes sense. Don't forget, this is a base, so you definitely want your pH to be over 7. That's one way of solving it. So we'll say 1. We also have another way to solve it, remembering that Kw equals, and you would have learned this yesterday when we were talking about the amphoteric nature of water, okay? Kw equals the concentration of hydrogen ion multiplied by the concentration of hydroxide ion, which is also equal to 1 times 10 to the negative 14. All right, so we already know what the concentration of hydroxide is, so we can use this equation. So what we can do is manipulate all right, we can do this. All right, because I got that from here, and there's my thing. So once I do that math, that gives me 7.46 times 10 to the negative 12 moles per liter. And then I just use the pH equation. All right, so I'm going to plug that into there. So once I do that math, so I plug it in, I end up with the exact same answer. And you should, because it's the same thing you're looking for. So 2 different ways to attack the same problem. All right, use one or the other. I don't care which one. So now one last question for this lesson. The last question, ooh, where did it go? Oh, that's fun formatting there. Okay, so let's take a look. I'm going to go back to purple. So now we're looking for the KB. So you're given some information here. We're going to be using a different weak base, methylamine. Bring back organic chemistry memories. Oh, that was the last time I saw you guys. Okay, anywho, we know that we've got a concentration of our solution is 0.1 molar. We know the pH, and this is at equilibrium. Okay, what's the KB? So we're looking for KB. So number 1, we can find out some information from this pH. So pH plus POH equals 14, right? So if I can solve for POH, then we can actually get the concentration of the hydroxide ion, right? So 14 minus pH, right? So my POH is 14 minus 11.80, which equals 2.20. Good. So now that I know my POH, my OH concentration, and we did an equation like this for Ka last lesson, is 10 to the power negative POH. Okay, so when we plug this in, 10 to the power negative 2.20, and make sure, don't just use my answer. Go to your calculator and make sure you can figure out how to do this to the exponent of a decimal. Okay, if you don't know how, take a picture of your calculator and I will show you how. I use an EE button. Okay, so when I plug it in, I get 6.3 times 10 to the negative 3 moles per liter. All right, so there's my concentration of hydroxide at equilibrium. So this is at equilibrium. Okay, moving on. Let's set up an ice table. So you're lucky. We love you because we gave you the formula, but that's not always going to be the case. Okay, so let's make our ice table. CH3, NH2, and I'm going to leave the agua out of it. Everybody knows why, but I'm going to say it anyway because liquid water has a constant concentration and is not included in any of the equilibrium constant equations. So back to this, CH3, NH3 plus my hydroxide concentration. Okay, let's get to it. Ice, ice, baby. So initial concentration we know from the question. We started out with 0.1 molar. Okay, we have not made product. My change, and we're so lucky because everything in this worksheet seems to be a 1:1:1 ratio. So I'm using it up so it's negative. I'm making it so it's positive. My equilibrium concentration, what I started with, how it changed, what it became, right? what I started with, how it changed, what it became. All right, so now I can actually, it's time for some, let's do it, people. Let's try a different one. I don't know, I've never tried this one before. Let's do it. So, once again, we know the concentration, that makes me so happy. Okay, we know the concentration of the hydroxide. So I can say that this value right here is X. So I can plug it right into there. I can plug it right into there. And lastly, I can plug this bad boy all the way into that X. Okay, let's not overuse the sparkle. It loses its panache after a while. Okay, so I know this X is 6.3 times 10 to the negative 3. This X is 6.3 times 10 to the negative 3. And this is now 0.10 minus 6.3 times 10 to the negative 3. And when you use your calculator, you will see that that actually equals 0.094. Okay, so now it's just a matter of solving for KB. So products over reactants. What did I do? Okay, there we go. So when I plug that in, this times this divided by this gets me 4.2 times 10 to the negative 4. And that's our answer. Well, that was easy. So now I'm going to highlight the homework. I urge you to read these sections because they've got additional examples that I'd like for you to go through and try these homework questions. Now, I've posted the solutions to the textbook questions within each content folder for each lesson. So you'll see those. This is the time where we would normally be doing a titration, and this is something that you know that I've talked about is very important. It's usually one of the first couple of lessons that you do in first year chem. So this equilibrium will not go away. Last year we did one with a strong acid base, and you know that the math is going to be easier because those go to completion and there's no equilibrium. So you don't have any ice tables, you have nothing. This year we would have done a titration with ice tables. Okay, so you will be doing this. Don't shortchange yourself. If you have questions, please ask. Okay, you can either email me directly through LMS or you can use the discussion tool. I will get back to you. Okay, keep working hard. Don't worry about the marks because at this stage of the game, I'm only going to help you. Okay, I want you guys to actually learn this and understand it. That is truly all I care about. So do the best you can and contact me if you need any help. All right, hope you're having a good day, and I hope that I will see some of you soon. Take care. Bye now.